Okay, so let's derive the famous bias-variance decomposition. So let's start with the assumptions. We are going to assume that we have our additive noise model. So our target, y, our output, is equal to some true function plus some noise. And we're going to make two assumptions about this noise. We're going to assume that conditional on x, the expected value of the noise is 0, and that it has constant variance conditional on x equal to sigma squared. So f of x here, I'm assuming, is our true function. And I'm going to label the estimator that we come up with from our supervised learning procedure f hat of x, the familiar notation that I've been using. So this is something that depends on training data. It's a random variable. So it's random in x, but it's also random in the training data. So once we have training data, we can think of this. Once we've learned it from the training data, we can think of f hat x for a fixed x, so not random, as our, well, that is our prediction rule, and that's a deterministic function. Or we can think of it as a random function of x. Right? So it's a random function, not a random variable, as I said a second ago. Okay, so what do we want to do in the bias variance trade-off decomposition, or trade-off or decomposition? What we want to do is we want to characterize this quantity here, the expected square prediction. So the bias variance trade-off, at least in its classical form, uses the square loss. So if you recall, we have different losses, different ways of measuring the discrepancy between a target y and our prediction using our prediction rule at some value x, right? And we call this a loss function. The classical one is L of x, L of y, f hat of x is simply y minus this squared. We call this the square loss. And this is the, this is the loss that we use in the bias variance trade-off, the classical one. And that's the one we're going to derive. We can extend this using what I believe Bregman divergences, but it's not particularly satisfactory, and we move to a different framework altogether normally. So this is the quantity that we want, the expected squared prediction error. Now this is across training samples, but it's also across test points, x, y. So these are points that were not seen during training. So let's remind ourselves of the setup in terms of the random sample that we have. We assume in linear regression, at least anywhere, and most regression, that we have IID random pairs xi, yi, and they're distributed according to some distribution pxy, some joint distribution. So these are pairs, they occur together, and they're sampled from some distribution pxy. And we have I equals one of these, and they are independent and identically distributed. They all have this distribution. And we go a bit further in the assumptions in that we assume these are the first n terms in a sequence. Sequence has an infinite number of terms, so this carries on, and it goes on forever. So the random sample that we're using or assuming, which is what generates our data set as realization. So our data set xi, yi, for I equals 1 to n, are realizations of these random pairs. And there's an infinite sequence of them. And the training sample is the first n. So a test point is any point that is subsequent to this. So not included in this. It could be any point. So when I say xy, I mean any one of the points along here. Subsequent to this point, xn, yn. So these form our training set. And any of these are our test points. So we have to do this because we need to ensure that they all come from the same experiment. They all have the same underlying probability space. So this is why one of the reasons we use this assumption. Okay, so now the test noise, what's that? Well, in our model, which is y equals fx plus epsilon, we can write this as epsilon equals y minus f of x. And as I explained before, we interpret y as the discrepancy between y and the true function. So it's all sources of randomness in the data generating process that we have not accounted for, right? And that could be noise, random noise due to random fluctuations. It could be unexplained variables. For example, this x here doesn't capture all of the information that we require in order to predict y. So there may be some missing predictors or regressors, as we would call them in statistics. So this epsilon is not independent of x and y. Epsilon, in actual fact, is a function of our random pair x and y. And that's what makes it a random variable. It's real valued and it's a function of this random pair, so it becomes a random variable. And this function is given precisely by this discrepancy between the outputs y and the true function values at some random x. Now, these are all IID. So any test point xy is going to be independent of our training sample. We can call it dn, and that's this collection xi, yi, these pairs, right? And that's from I equals 1 up to n, the index set here. So this is our training sample, and any test sample, which is any one of these, is independent of this. These are independent. So this expectation that we're taking is over two things. It's over the training data set and our test random pair or observation xy, which is independent of this. So when I wrote down that we want to calculate, let me just remind you, this expectation here, this expected square prediction error, this is across training samples, so the dn, and also the test points. So it's across both. So this expectation is basically with respect to a joint distribution, not basically, it is with respect to a joint distribution of the training sample and some random test pair. So it includes randomness due to our choice of training sample and also due to our choice of the test point, because we have many test points that we can choose from in the whole population. Now let's substitute into our expression, not straight away, but we're going to start decomposing it. So what we want to find an expression for is this, the expected value of y minus f of x, f hat of x, our predictor, all squared. We want to know what this thing is, right? So in here, what do we have? We have y and f hat of x. So let's replace y with what we have based on our model, that y is the true function value plus the error. And what do we get? Well, we get this quantity squared, which is what appears in the expectation, is so y is just f of x plus epsilon minus this thing squared, which we can write like this. So what do we have here? We have the first term here, this minus this squared. We're grouping these two together. Then plus 2 times epsilon times f minus f hat, which is what we have here, plus epsilon squared, which is the third term here. So this cross term here is what we're initially going to focus on, because it will turn out to be 0. and we have to see why it's 0. So now before I show this, I should mention one thing. So we're trying to show, or we're trying to get a handle on what this quantity is, the expected value of y minus f at x all squared, right? Now, normally in the literature, you will see this not in this form. You won't see an expression for this. What you'll see an expression for is the expected value of the same quantity. But now let me put y minus f hat, or capital Y minus f hat of x, little x, all squared, given a value x equals x. So pointwise, we normally see it in this form. So given some value of x, what is the expected value of this, right? Now that expected value is over the training samples. That's what you're looking at in that case. So here it's over the training samples and xy, right? Here we're looking at it only over the training samples, given x, right? So this is the way that we normally see it written. So I'm going to instead derive that global version that I wrote down first. And then at the end, we will see how this very easily we can write in a pointwise form, which is the more familiar form that we see in the literature. So let's tackle that cross term. We're going to use two facts. Our assumption about the noise, that conditional on x, it has a 0 mean, and also that epsilon, which is a function of y and x given by this precisely this function here, is independent of our training sample. So we're going to use these two facts here. So what do we want? We want the expected value, and this is the expected value over the training sample and x, y together, right? So it's the expectation over these. So we can decompose this expectation using the tower, what we call the tower property. What I'm using here is the tower property, right? Which tells us that this expectation over this, the joint distribution of the random sample and this random pair, is the expectation over the joint distribution over this and this of the expected value with respect to only y of the same quantity, given x and the training sample, right? So this is what we call the tower property. Basically, it's a very simple decomposition. So this is in the probability slides, and I mentioned it ubiquitously throughout the probability videos. So from here, where do we go? Well, this doesn't depend on y, right? The only thing that depends on y is this epsilon, right? Because epsilon is y minus this thing here. So we can take this outside the expectation, which is what I've done here. And we're left with this times the expected value over y. I should put here given x and this as well, but it doesn't really matter. Of epsilon given x and the training sample. But epsilon is independent of the training sample. So this becomes, so going from here to here, all I've done is got rid of this training sample here, this training sample conditioning, because epsilon doesn't depend on that. It's independent of that. It depends only on x, right? So, but this is 0 by our assumption. And so what we get is the expected value of 0, which is, of course, just 0. So this cross term that we wrote down, let's remind ourselves of what we did. We want the expected value of this, and we wrote it like this, with these three terms here. And so if we take the expected value of this, it's going to be the expected value of this plus 2 times the expected value of this plus the expected value of this by the linearity of expectation. But the expected value of this, epsilon times this, we've just shown is 0. So we're going to end up with just the expected value of this plus the expected value of this. So, which is what I've written here. So the expected value of this thing squared is now the expected value of this plus the expected value of epsilon squared. Now, leave this alone. Let's focus on this term here. This is the expected value over x, because this doesn't depend on the training sample. This depends only on the random pair. Epsilon depends only on the random pair xy. It's independent of the training sample. So this expectation here is basically an when we pass it through this plus this part, which starts out as being the same expectation, becomes an expectation only over the random pair, which, again, using the tau property, we can decompose as the expected value over x of the expected value y given x. Here I've written the conditioning properly, of epsilon squared given x. Now, what is this? Well, let's think about this. The expected value of epsilon given x is 0, right? So what would be the variance of epsilon given x? Right? That would be the expected value of epsilon squared, not epsilon squared, epsilon minus the expected value of epsilon given x, all squared, right? But this is 0, right? So this disappeared, and so we end up with the variance of epsilon given x is the expected value of epsilon given x, right? Squared given x, which is exactly what we have here. And so this thing here is the variance of epsilon, the conditional variance of epsilon, which is constant. It doesn't change. It's always sigma squared, a constant. So this is sigma squared. So its expected value over x, because it's constant as a function of x, is also sigma squared. So we end up with these two terms here. Okay, now we're getting closer to where we want to be. So we've got to this point here. So what we need to do now is take care of this term here. Now I'm going to simplify the notation a bit by defining the following quantity here, f bar of x, as the expected value over the random sample of our predictor f hat of x given x, right? So this is the expected value of the prediction across all training samples. So given some value of x, so I can write here, given some value of x equals x, what is the expected value of f hat of x, right? Now, f hat depends on our training sample. So if we change training samples, we're going to get a different predictor. And so we're going to get a different value, f hat of x. So this quantity is saying what is the average over all of the training samples, all possible training samples of f hat of x, right? Where x is some value that we fixed our random input x to. So this is what this quantity is here. We don't have to define it like this, but it certainly simplifies the notation. And also, I did it because otherwise I can't fit everything across here. It's simply too long. So having defined that, now let's go back to what we want to focus on. We want to focus on this square here now. So let me rewrite this square using a little trick. I'm going to rewrite, not the square, the term inside the square, using this trick. So this term here as f of x minus this expected prediction plus the expected prediction, so these two just cancel, minus f hat, which of course just gives us back to this. This is just a trivial identity. But it's done for a reason, because we want to decompose this into parts that we can understand or model. So then our square, the square of this, becomes the square of this, which is what's the square of this, which is what I have here, plus the square of this, which is what I have here, plus 2 times this, which is what I have here, the cross term. So let's now focus on this cross term, right? So again, this will turn out to be 0. Let's see why it's 0. So what we're going to do, well, we need to take the expected value of this, right? So we're going to take the expected value, sorry, of the square of this thing squared, which is the expected value of this whole thing now. So it's going to be the expected value of this plus the expected value of that plus twice the expected value of this. So let's find out what the expected value of this is. So this expected value is with respect to the joint distribution over random sample and our random input x, because this does not depend on y. So we could put the y in there, then we'd have an integral over the marginal over y over the whole value space for y, which would just turn out to be 1. Right? So our normalizing constant would be 1, so we don't need to include it. We only need to consider the random sample and x. So let's figure out what this expectation is. Now, again, x is independent of our training sample. So what do we get? Well, let's use the tower property again. So now we have only x and dn, as I explained. So the outer expectation, let's take that with respect to x, and the other one, the inner expectation with respect to the random sample. And then we have to condition on x when we do this in the tower property. So it's the expected value of this over the training samples. Now this doesn't depend on the training sample at all, right? So once we've fixed an x, what is the randomness in this? Well, there isn't any, right? Why? Because f of x is our true function. Once we've fixed x, that's no longer random, right? Conditioning on x, once we fix x to some, let's say, little x, that just becomes f of x, and that's not random. What's f bar of x, little x, once we condition on x? Well, that is, it's the expected value over all training samples of f hat of x, right? That's what this is, given x equals x. Write it like this, or I can write capital X here and just x without the equals x here. So that's what this is, but we've already taken the expectation with respect to the training sample. So this doesn't depend on the training sample either, f bar. So we can push this through here and apply it only to this term, because this has no dependence on the training sample. So we've got the expected value of x of this thing times the expected value over the random sample of this quantity here, which does depend on the random sample, conditioned on x. The expectation is conditioned on x. Now, again, this doesn't depend on the random sample, but this does. So we can push this through. So this just becomes this minus the expected value of this conditioned on x, which is what I've written here. And what is this? This is exactly f bar. That's how I've defined it. So we end up with the expected value over x of this thing here times f bar of x minus itself, which is obviously 0. Right? So we get expected value of x of 0, which is, of course, just 0. So again, this cross term disappears. Okay. Now, what do we have left? Well, let's remind ourselves so we don't lose track. here, we have these two terms here. So we've got this term and this term. We've got rid of this term. So now we've got expected value of this plus the sigma squared that we had from before. So let's now focus on these two terms here. And which one am I doing first? So I'm doing the second one here first. The expected value of our predictor minus this average value, its average value, right, over all training samples. So let me write that out. So this was defined as this, right? So we've got, and now I can use the tau property again. And I'm doing this, we don't have to do this, but I'm doing this because in the end we will end up writing the pointwise version of the bias variance trade-off. So we need to extract what's going to be inside here. So using the tau property, this is the expected value over x, right? Because what do we have here? Well, this is an expected value over dn and our random pair xy, the joint distribution of these two things here. But this doesn't depend on y, right? So this is only over the joint distribution of this and x. So we can use the tau property again. So we've got on the outside, the outer expectation is with respect to x, and the inner one is with respect to our training sample. And what is it? Well, it's f hat of x minus this quantity here conditioned on x. And what is this? This is the variance of our predictor f hat of x conditioned on x. It's conditional variance, right? And what does it represent? Well, it's the variance as we vary the training samples. So for different training samples, we're going to get different f hat of x at any given value of x, right? And the variance in that is defined as follows, right? So this is with respect to the training sample. And this quantity inside here, we call it literally the variance of the predictor. And it is, we don't call it literally, it is literally the variance of the predictor. And we call it, therefore, the variance of the predictor. Although, to be technical about it, it's the conditional variance, conditioned on x. Okay, so that's the first thing, the first square term. And we call this the model variance. So this is often when you hear the term model variance, they're referring to this. They're referring to the variance because it's often a bit confusing, not often actually, when you first look at it, it's confusing to work out what is going on and over what quantities are we taking expectations, etc. And when we say variance, with respect to what? It's with respect to the training samples, not with respect to x or anything else, with respect to the training samples. So given some value of x, what is the variance in our predictor? Variance in terms of the distribution over the random sample, right? As we change the random sample, the realizations of it will get different predictions. And it's measuring the spread of those predictions, the variance. So that's the variance. So, and now we're on to the last term. Well, what is the last term? Well, it's the expected value of this square here. What's this? This is deterministic, right? Once we fix x, this is entirely deterministic. So this here depends only on x. This quantity here, we know that is, so for certain, this is independent of y. And this has dependence only on x. Once we fix x, this is totally deterministic. What about this term here? Well, we've already seen this is the expected value of our predictor over training samples. So this has no dependence on dn and no dependence on y. So let's get rid of those. Has dependence only on x. So both of these depend only on x. So this expectation, so the other dependencies would just be integrals over, the training sample and over y, and they would just integrate to 1 in both cases. So what we end up with is just the marginal, the expectation only over x of this quantity. And we can write this as well by reintroducing the definition of this. It's the expected value of our predictor. And this term here, for a fixed x, we call the bias of our predictor. Right? And the bias of a predictor, as we've already seen, is how far it is from the expected value. So a predictor or an estimator, we call it predictor. In this case, we tend to call it a predictor, but generally in statistics, we have estimators which estimate some parameter. The bias of that estimator, so if we have a general estimator, let's say theta hat, right, which depends on some IID sample, and that theta hat is estimating some true parameter theta, right? This is random because it depends on a random sample. We say that the bias in this estimate is the expected value of theta over the random sample, all random samples, the average over random samples, minus theta. It's this discrepancy. And this we call the bias of our parameter theta. Well, it's the same thing here. This here is the bias in our predictor. It's the expected value of a predictor minus, for a general x, minus the true value at a general x, right? Sorry, conditioned on some x. So this is for some, usually at some fixed x value. That's how we define the bias. So let's say this measures how far on average this estimator is from the true value. In our case, how far on average our predictor is from the true value. So, importantly, it's the thing inside which we're squaring. So this is the bias. So what we've got is the square of the bias, or the bias squared. And so for what we call an unbiased estimate, we covered this already, these two would be equal. So the bias, in other words, is 0. So unbiased estimator or predictor means 0 bias. The expected value of that estimator or predictor is equal to the true value. So finally, we've come to our bias variance decomposition. The expected value over training samples and test data of this square error, the true value minus our prediction at x, is equal to the expected value over x of this quantity here, which is the square bias, plus the expected value over x of what we call the model variance, plus sigma squared, right? Now, we usually write this pointwise, meaning we condition on some value x equals little x, in which case we end up with this pointwise version of this. So we're just so we're conditioning. I'm leaving out all of the given x equals x and all of that just to simplify the notation here, and I'm not writing in the subscripts here. What we end up with is the expected value over the random samples of this squared error is equal to the model bias squared plus the model variance plus what we call irreducible error, error due to noise, right? Noise in our sampling. So this error comes from what? This error comes from the sampling the point xy. When we sample this point xy, we introduce some error, right? And that's captured in this noise term epsilon, right? And that error is unavoidable, and it leads to this term sigma squared in this bias variance trade-off. So we call this the bias variance decomposition or bias variance trade-off, or that might actually refer to some analysis that people do. Normally we just call it the bias variance decomposition, but you could also refer it to it as the bias variance trade-off. So let me discuss these terms a bit more to end this part. So the first term, so first of all, there are three sources of error, as we've just seen. Right? So this expected square loss is a prediction error. What is the error in the prediction at some x fixed x equals x? Right? Measured as the square of the difference between our true output, our measured or observable y, and our prediction f hat of x. And it has three components. The bias. And what does this come from? Well, first of all, it looks like this. It comes from what we can generally call model misspecification. So an incorrectly specified f hat. Remember, we have to choose some model for f hat, whether it's linear regression or some non-parametric model, whether it's a neural network, whether it's a kernel machine, whatever it is, we have to choose some model. Now, in the unbiased case, the expected value of that model would be equal to the true function at each x. But it may be that we choose a model which is far away from the true function. We choose a hypothesis class. Right? In our ERM framework, we saw that basically this comes from a hypothesis class. So a simple example is, we use a linear model here, linear in x, I mean here, whereas the true function f hat of x is a nonlinear function of x. So this we call model misspecification, and we refer to this kind of loss as the bias. Then we have model variance, and this is due to sampling variability, meaning the random sample that forms our data set. Right? And it's this quantity that we write, it's the quantity that we write like this. And typically, and we saw this in the examples, in polynomial examples at least anywhere, and I explained it in quite some detail, and we will keep seeing it again and again. This is highest when we have models, our f hat, living in hypothesis classes with high capacity. So for example, if we use a 20th order polynomial, right? That's something, or the set of all 20th order polynomials, that would be our hypothesis class. It's very complicated. It's able to adapt to noise, as we say. It can fit noisy patterns quite well, or certainly much better than, say, an affine function or a quadratic function. And in that case, we can have this simple relationship between model capacity and number of parameters. So a 20th order polynomial will have 21 parameters, including the bias term. And in that case, in this linear regression case, we have this very tight relationship between model capacity, how easily our functions in our hypothesis class are able to fit to random noise, and the number of parameters. So as a general rule, the higher the capacity of the model, the higher this component of the error is. This error tends to come when we have models that are too simple, low capacity, or lower capacity than is actually required, because then we are far away from the true function. So this was an example where we're using a linear model in x, linear in x, in this case, to model a function that is nonlinear in x. So for example, if we use an affine function, right, like this, to model e to the power of x squared or something, right, or minus x squared. That's totally unbounded. It would go to infinity very quickly. Not infinity, but large values. So if we use something of this form, a plus bx, to model something of this form, this is So all functions of this form form a space which we call a hypothesis space or hypothesis class, which is of low capacity. It's of dimension only 2, right? It has 2 degrees of freedom, this A and this B, right? Considering um, basis functions of 1 and x, right? Whereas this is a function that lives in a space of much higher dimension, of infinite dimension, in actual fact. So we can't hope to capture something like this with a hypothesis class of functions like this, right? So here, the model capacity is too low, and we would have a high bias. But a low variance, by choosing simple models like this, as we change the training samples, these A and B values will not change very much because we only have 2 values to fit. Right? Now, if I extend this to a 20th order polynomial, a20 x to the power 20, right? Now we've got 21 parameters to fit. So as we vary our training sample dn, we will come up with there'll be much greater variability in these parameter values that we find across different training samples. So this error is going to be higher, right? But this will be lower because this kind of polynomial is much more likely to be able to fit within some specified range of x, even a function like this, right? So that's the general rule. Low complexity model or low capacity model means low bias, high bias, low variance, and high capacity means low bias but high variance. Okay. And then the final component is this irreducible noise, which comes, as I say, from the intrinsic randomness in the data, meaning the random sample XY, our test data. And this is something we cannot get rid of. Hence the name irreducible. So the 2 components of error in regression, at least with the square loss, which is what we typically use, that we try to focus on, not that we do focus on, are these 2 terms. And there's usually a trade-off in that, and I've just explained this, perhaps I can just show it pictorially. What tends to happen as we increase the complexity, so let's say complexity is going this way of our model, and this way is the error. What tends to happen is that as we start with a low capacity, the error is high, and then it decreases, right? And it reaches some point where we get minimum error. So here we've got the minimum error. Then what happens is as we further increase the complexity, which is along this axis, this term starts to dominate. So down here, what's happening is this term is dominating. Once we get to here, the minimum, this term starts to dominate. This becomes much lower, but this starts to dominate. And that starts to rise. And so what you end up with is this situation where you reach an optimal complexity, right? Let's call it C star, optimal complexity. And if we go any higher in terms of complexity, for example, we're using a polynomial and we go up to some degree n, right? So that would be this, there would be some n star, some ideal polynomial degree, and lower than that would be in this regime here. We'd have high model bias, but low model variance. Then we'd reach this optimum, and then the model variance would start to increase as we go n greater than this, higher order polynomials. This would not increase, this would be generally low, but this would be high, and it would start to could increase quite rapidly. And so we find this sweet spot here. Right? Now, it's usually not that sharp. There's some sort of, wiggle room around here, right? But you want to be in this general ballpark here. You don't want to be down here, and you don't want to be up here, right? So this is what the what they often call the trade-off, bias-variance trade-off. It's in terms of complexity. So we don't want a complexity which is too low, and we don't want one which is too high. But this is not always. This is not a foolproof way of looking at it, because in very deep networks, for example, we have what's called a double dip phenomenon. So we might get this, and then it might go up, and then it might start to come down again, right? Get a double dip. I won't discuss that here. We'll keep things quite simple. So anyway, that's the bias variance trade-off, and I will stop there.